Hi, welcome to videos on feedback amplifiers. This is the fourth video on this series. So in this video we'll see the types of feedback that are employed for amplifiers. This is an amplifier with feedback. If you can see, A is the amplifier, beta is the feedback network that is used to provide some portion of the feedback back to the input. We have the source and the load for the amplifier circuit. This is one of the feedback topology, which is called as series-shunt feedback. In this series-shunt feedback, the phenomenon, what we are doing is we are mixing the voltage and sampling the voltage. Since voltage is mixed and sampled, so it has to be from an amplifier which accepts the input voltage and whose output is an voltage which happens to be from a voltage amplifier. Since voltages are always sampled in shunt, so that's why we have a shunt connection at the output, and voltages are added always in series. We have a series connection at the input for adding the voltage. So we have voltage mixing and voltage sampling. The required amplifier is voltage amplifier. So the type of topology that is followed in this case is series shunt feedback. So why it is called as negative feedback means because of the polarity of the feedback voltage, how it is connected in series with the supply voltage. So this is the input voltage that is applied to the basic voltage amplifier. If we can write the KVL for this particular input loop, the input voltage VI that is being applied to this basic voltage amplifier happens to be the signal voltage, that is Vs minus the feedback voltage, which is Vf. Suppose the polarity of this is plus minus, then this will be called as a positive feedback. In such case, the feedback voltage will add up with the already existing source voltage. So with this polarity as minus and plus, it is called as negative feedback. Let us see one of the practical circuit for this using op-amp. So as we are sampling the voltage and we are adding the voltage back to the circuit at the input, again applying the KVL here. So the applied input voltage to this amplifier is V supply minus V signal minus the feedback voltage. So that's why it is negative feedback. And since we are sampling the voltage and adding the voltage, it is series shunt feedback. And one more such example is using MOSFETs. So where we have a source degenerated CS amplifier followed by a CS amplifier. The output of second CS amplifier is applied at this point. Now here you are sampling the voltage and applying a portion of it as the input voltage for this, which will actually subtract with this Vs. So that's why this V input voltage that is applied to the MOSFET is Vs minus Vf. So it's again a series shunt feedback amplifier. So we will see another type of feedback topology where we are this is called as shunt series feedback. So why it is called as shunt series is because you can see at the input side you have a shunt connection, at the output side you have a series connection. So since we are sampling the current here, so that's why it is in series, and we are adding the current, so that's why it is in parallel. So that's why it is called as current mixing and current sampling. So you are mixing the current at the input and sampling the current at the output. So this basic amplifier has to be a current amplifier which can allow sampling of the current and adding of the current. So that is again done using a feedback network. And why it is again called as a negative feedback means because the current whatever that is going into the basic current amplifier circuit is source current minus the feedback current. So this is a current that is flowing into the amplifier network. So that's why it is called as negative feedback amplifier with this is shunt series feedback or current mixing and current sampling feedback. We will see a particular circuit to represent this type of topology. You can see this is shunt series feedback. Whatever that we are applying here, you can see this is the current that is being applied. If you can see, this is the output current. Whatever input current that you are applied here, is going here I and this is IF, and this IF depends on what is I naught. So because you are sampling some output current and you are adding that current over here with this negative polarity, so that's why this is called as shunt series feedback, because output current is sampled and output current is added, a portion of that is added with the input with appropriate sign of minus. So here you can see, if we can actually find out what is II, the current going into the amplifier is actually IS minus IF. Of course, we can find out what is the magnitude of this current looking into this I naught and these resistors. The third category is series feedback. Again, the name series is you are adding the voltage here and you are sampling the current. So it is voltage mixing and current sampling. So since at the input you have voltage, the output it is current, so this has to be a transconductance amplifier. So for this transconductance amplifier, the expected or the desired feedback topology is series feedback, because the voltage is added in series and current is sampled in series. And again, this is negative feedback because the applied feedback voltage is actually Vs minus the feedback voltage at the input side of this amplifier. Again, the corresponding circuit for this is, if you can see, this is I naught, the current, output current. A fraction of that is sampled here. You can see this is the feedback voltage. Since Vi is Vs minus Vf, it is a negative feedback, and the output is current, so that's why it is a series feedback. Output is current, current you are sampling, and then you are adding the voltage back to the circuit with negative sign. Next is shunt feedback. As it is clearly said that when it is shunt feedback, you're going to have the current being, voltage being sampled, and then we are mixing the current here. So current is mixed here and voltage is sampled. So that's why at the input and output you have the shunt connection. That it is called as shunt feedback. Since the input is current, output is voltage, so this has to be a transfer resistance amplifier, and the corresponding feedback network will give a current proportional to the desired voltage what you have. The corresponding circuit, a possible circuit will be, so you have this is the current that you are, so you have sampled the voltage. So what you want to have is, you want to sample the voltage and add the current. You can see this is the sampled voltage what you have, and that will be fed back to the input with appropriate sign. Suppose if you again find what is II here, II is actually IS minus IF. So that's what we saw here. So this whatever current that is going inside is IS minus of IF. So this is the current that is going into the circuit. So that's why it is negative shunt feedback. But in this particular course, we'll not be referring to all the categories, all the feedback topologies. We'll be concentrating only on series shunt feedback amplifiers. So we'll do a detailed analysis of series shunt feedback topology. So this is what is a series shunt feedback circuit having an ideal source, and of course there is an ideal load. The load is actually open circuit, and we have a ideal amplifier. So let us assume that this Ri is very large and this R0 is very less, and we have an ideal feedback network which is not loading this output, and you can see this is actually making this minus plus. So this is actually effectively doing the negative feedback for this particular amplifier. So let us start representing this amplifier after feedback, how it looks like. So this is an amplifier with source and load and with feedback network, and this can be effectively represented by only one input source, that is called as RIF. This RIF happens to be the input impedance after feedback. Again, ROF stands for the output impedance with feedback. AF is actually the amplifier gain after feedback. This is after feedback, whereas this A is the open loop gain without feedback. So this AF, as we earlier discussed, AF is equal to A by 1 plus A beta, because we are giving a negative feedback, so that's why it is A by 1 plus A beta. Of course Vs is the supply voltage what we have. Okay, let us try to see how do we find the value of RIF. So you may remember that one of the advantage of going for negative feedback is it improves the input impedance. Let us analyze that how it improves the input impedance. So we know that the feedback amplifier gain AF is equal to A by 1 plus A beta. If you can carefully notice here, if you write the KVL for this, the input voltage is equal to the input voltage at the amplifier input is equal to Vs minus Vf. So this is what is Vs minus Vf. But this Vf is actually derived from V0, so it is beta times V0. So that's what we are writing, Vf is equal to beta times V0, where this V0, whatever output voltage you have, is actually A into Vi. So this is V0, which is A into Vi. That's what we are trying to do. So this V0 we are replacing it by A into Vi. So ultimately writing input voltage as Vs minus beta times AVi. You can write it as now I can write the expression for Vi or Vs as Vs is equal to Vi times 1 plus A beta, or ultimately I can write Vi by Vs is equal to 1 over 1 plus A beta. So this is a relationship between what is the input voltage and what is the source voltage, that is before you just before the feedback network. So this is your Vs supply voltage, this is Vi. The relationship is it is 1 over 1 plus A beta, meaning to say if you don't have the feedback, whatever is your Vs will be reaching Vi. Since you have a feedback here, the input voltage that is reaching Vs is reduced by 1 plus A beta times. So actually your input voltage will going to reduce by 1 plus A beta times. Again, moving on to find what is RIF. So we have this expression, we have derived this expression, okay, Vi by Vs is equal to 1 over 1 plus A beta. But if you can see, this is we are seeing the input voltage looking from this point, looking into the network. This is called as the input impedance considering the feedback network. So this is RIF, which happens to be Vs by Ii. So this is what we are supposed to find, is it is Vs by Ii. But we know that if this is Vi and this is Ii, Vi by Ii happens to be Ri. So that's what we have written here. Vi by Ii is Ri. We want to replace this Vi, whatever Vi we have here. You can see we have an expression for Vi here. So I can write what is the expression for, I am rewriting it as, since I know, okay, the input impedance of this amplifier at this point, Ri is equal to Vi by Ii. So that's what is Ri is equal to Vi by Ii. But try to replace this Vi by this expression. So can I write Vi is equal to Vs by 1 over 1 plus A beta? So that's what is done here. This Vi is replaced by Vs by 1 plus A beta from this equation. So from which we can say that, of course, I can rewrite this expression as Vs by Ii. So Vs by Ii is actually measured from this point, is actually this ratio of Vs by Ii is RIF, and of course you have 1 plus A beta as it is. So we have replaced Vs by Ii as RIF. So by rewriting this expression, I can write RIF, which happens to be the input impedance with negative feedback, happens to be the input impedance multiplied by 1 plus A beta. So this is the input impedance of the amplifier without feedback, and if you are measuring from this point, you can see when you are seeing from here into the network, this feedback network is also included. Since you are seeing from this point into the network, it is the input impedance with feedback, that is RIF, which is given by Ri multiplied by 1 plus A beta times. So meaning to say, the input impedance of an amplifier will increase because of negative feedback by an amount equal to 1 plus A beta. So using this, we can actually increase the input impedance of an amplifier, which is good for an amplifier, which is close to the idealness.